Okay, welcome to all of you, also from my side. I will give a kind of introductory lecture about the solar-wind magnetosphere interactions. I hope this thing works. No, it doesn't work, of course. Why not? Yeah. Okay, so there will be actually 2.5 parts of this lecture. I will first talk about a bit about, I will assume you don't know anything about space weather and magnetosphere. So I will not throw a bunch of equations to you. I will try to keep it light, certainly for the first lecture. And I will first talk about space weather, what it is and why we want to study it and predict it actually. And then I will focus on the magnetosphere and then about the interactions of the solar wind and the magnetosphere and how we can try to quantify these interactions and to model them and to predict them. So, as you may know, the solar wind is a continuous stream of particles leaving the sun. The sun loses like 10 to the 9 kilograms per second of plasma, which is kind of ignorable if you count the total mass of the sun. Here you see a nice illustration from Craig DeForest in 2018, which is unprecedented resolution by using a co-moving frame averaging of stereo A images. The solar wind fills the entire solar system, which is called the heliosphere, and these particles are low energy particles. They have energy between half to 10 kilo electron volt. There's actually two kinds of winds. It's a bimodal wind, so you have the slow and the fast wind. Slow is relative because it's still 300 kilometers per second on average, and the fast wind is 750 kilometers per second. But the velocity is not the only part distinguishing between the two. There's also different chemical composition because they originate from different regions on the sun. It drags out the magnetic field because the sun is rotating, so you get this spiral structure of the interplanetary magnetic field due to the solar rotation. Now, on top of this wind, we have transients like solar storms, like the coronal mass ejections, which are enormous clouds of hot plasma illustrated there on the left, which are launched into space at typical speeds of 450 kilometers per second. But it can range between 350 to 3,000 kilometers per second, which is more than 10 million kilometers per hour. And we also have the solar flares, which are intense releases of high energy radiation like EUV, X-rays, gamma rays, like illustrated there on the left-hand side also. Solar flares accelerate particles because of a magnetic reconnection, disconnecting magnetic reconnection events, impulsive solar energetic particle events, as they are called. Now, the CMEs that I mentioned before also can accelerate particles. This is an illustration of how a CME is looking like. I hope I can, yeah. So you have here the kind of a flux rope, and it's going so fast that it creates a bow shock before this flux rope, and in this bow shock, particles are accelerated. And the particles are, of course, it's very hot plasma in the corona, so there are electrons, protons, and heavier ions, and they have much higher energies than the background solar wind, so kilo electron volt to giga electron volt. And 1 mega electron volt proton travels at 14,000 kilometers per second, while a giga electron volt proton travels almost at the speed of light, so a huge difference, much more energetic than the background solar wind particles. There are charged particles, of course, so they feel the background magnetic field, so they make this spiral movement around the interplanetary magnetic field lines. That's why it is very important to know the magnetic connectivity between a satellite or the Earth with the surface of the sun, because we know if there are particles accelerated, you can actually, if you know the connectivity, you can already predict if they are going to be dangerous for our technical equipment, yes or no. Then we come to the definition of space weather. There are many different definitions. The one that I like the most is the one that is used in the strategic plan of the National Space Weather Plan in the USA. where it states that space weather, the term space weather refers to the conditions in the sun and the solar wind, but also in the magnetosphere, the ionosphere, and the thermosphere of the Earth that can influence the performance and the reliability of our technological systems, both spaceborne or ground-based, and can also endanger human life or health because of the radiation, of course. One of the most important events causing the space weather are the coronal mass ejections. Especially here you see kind of a speeded up movie of the during solar maximum in August 1999. And you see there are many of these CMEs per day. This is a white light image from a coronagraph. So the sun is covered by a disk, and then you can see the corona in white light, because normally the photospheric light is so intense it is blinding. You cannot see the corona in white light, but with the coronagraph you can. And so about 10% of all CMEs affect the Earth in some way. And so that means like 1 per week during solar maximum. CMEs, as I said, they go typically at 450 kilometers per second. It's a huge amount of mass. So the large CMEs are 10 to the 16 grams. I was told this is comparable to the mass of the Himalaya. Yeah? And so if you accelerate this kind of mass to these velocities, you need a lot of energy. And so for the bigger CMEs, it's like 10 to the 33 ergs, which is kind of 5,000 atom bombs or so. So it's a huge, these are the most violent events in the heliosphere. Nevertheless, they were, well, not to say discovered, the term CME was only used in the 70s, analyzing data from the OZO-7 mission by Bruckner et al. I think they were the first to use the term CME, coronal mass ejection. The effect on Earth is, of course, important, and here you see a simulation of the magnetosphere of the Earth, and because the wind with all these ranges is not uniform, there's a kind of a time dependence, yeah? So the magnetic field of the Earth is reacting to this varying dynamic pressure of the solar wind, and you know from Maxwell's equations, if you change a magnetic field in time, you induce an electric field. So on Earth, there are electric fields induced on everything that is long and conducting, like pipelines, oil pipelines, or the power grid, even long bridges. We sometimes see these geometrically induced currents. And this is, of course, not good. This is affecting our technology. So there's a lot of damage caused by the space weather. And here you see kind of a slide that I borrowed from Juha-Pekka Lontama, the head of the space weather division at ESA. And here you see kind of a summary of what coronal mass ejections and these energetic particles can do. And there's a lot of systems. I'm not going to go too much into detail, but I mentioned the pipelines and the geometrically induced currents. But of course, there's also radiation. So we are, of course, here protected by the atmosphere and by the magnetosphere. But the higher you go in the atmosphere, the less protected you are. And so the passengers and the crew of higher flying planes, and airplanes always try to fly higher because there's less drag, of course. So especially the one that do intercontinental flights that go over the 67 degrees latitude band, there have during a storm can get kind of radiation dose. I was told that during a severe storm, if you're in that position there, you can have a dose that is comparable to an X-ray photograph of your chest. That is okay, once per year, but not too many, because it's accumulating, of course. There's other effects. I'm not going to go too much into detail, but of course it's clear that the instruments on our satellites are the most vulnerable because they are higher than in the magnetosphere or located depending on their orbit, of course. Now, the average damage on our technology is estimated to be 10 to the 10 billion dollars per year. That's the average during normal space weather conditions, but it was also estimated by Eastwood et al. In 2017 that the economic cost of one extreme event can be up to $2.7 trillion. This is a lot. This is 15% of the GDP of Europe from 2023. So this is really, this is for a single event. And the recovery time, reporting that paper, would be 6 to 10 years to repair all the damage. So clearly we want to kind of predict this, to kind of mitigate some of the effects. Not everything can be mitigated, but some of the effects can be mitigated. And there's a link to climate. Well, the space climate is linked to the climate at Earth and to climate change. Actually, I don't have time to go into detail, but there are people investigating these links. Very complicated. The only positive effect about space weather is the aurora. So, so here you see the aurora from the space shuttle, and this is the only beautiful effect. And these also we try to predict, of course, for tourism industry. So the magnetic field of the Earth is generally a kind of essentially a dipole, but of course, because the solar wind, as I mentioned, is also magnetized, the interaction of this dipole with the solar wind is kind of complicated. And the complication you can see also in Ganymede. Ganymede is a moon of Jupiter, which also has a dipole magnetic field, but it is located in the magnetosphere of Jupiter. Yeah? And so there the wind is already decelerated, and so there the interaction of this wind with the dipole of Ganymede is subalfenic. It's a subalfenic plasma flow, and so that there you can see that you have these wings, Alfvén wings they are called. And so in these wings the magnetic field changes direction, and also the velocity is lower, as you can see here. This is a cross-section over here. So these are the boundaries of these wings. Now, why am I telling this? This is only when the wind is subalfenic. Now, of course, at Earth, the solar wind is usually, most of the time, superalfenic. And to find a way around this dipole of the Earth, when at these velocities, the angle is too big for an oblique shock, so it makes kind of a bow shock, detached shock. Although sometimes at Earth we have papers, I think in 24 and 25th of May 2002, the solar wind was subalfenic. So you also had these Alfvén wings at Earth. But this is very rare at Earth. It was because the wind was induced in 2002. Generally, there was very low density, and when density is low, the Alfvén speed goes up, and the wind became subalfenic, and then we had also the Alfvén wings at Earth. But generally speaking, normally at Earth the wind is superalfenic, and you have this bow shock that is formed. So this is the bow shock, a standoff shock, disconnected from the dipole, and so this is the bow shock. This is the outer layer, or the boundary of the, let's say, what we call in general the magnetosphere. So this is because the wind is superalfenic and super fast. It's the outermost layer of the magnetosphere, and it is due to the interactions with the bow shock, the solar wind plasma becomes anisotropic, which leads to various plasma instabilities upstream and downstream of the bow shock. Now, behind the bow shock, you have the so-called magnetosphere, which is indicated here, number 2. This is between the shock and the magnetopause. In purple is the magnetopause. And so this contains actually mainly decelerated plasma from the solar wind, but also a little magnetospheric plasma. And it exhibits a high particle energy flux, and the direction of the magnetic field is kind of erratically varying in this magnetopause. The magnetosheet, sorry. And then in the magnetopause, this is the purple, in this cartoon, purple area. This is where the dynamic pressure from the magnetospheric wind is, from the magnetosphere, the dynamic pressure from the wind is balanced by the, that is an error, sorry, is the pressure from the magnetosphere is balanced by the dynamic pressure from the solar wind. This is wrong, sorry. It's also where the shocked solar wind from the magnetosheet meets the magnetospheric field and plasma. The structure of this magnetopause is varying because it depends, of course, on the Mach number of the impacting solar wind, but also on the plasma beta, the ratio of the thermal pressure and the magnetic pressure, and also on the magnetic field, the orientation of the magnetic field also. The size and the shape of course, vary of this magnetopause as the dynamic pressure of the solar wind is fluctuating, as we have seen in this illustration before. The magnetosphere itself is actually the compressed magnetic field. This is what is indicated, everything within the blue contour lines here is the magnetosphere. And you have, well, here in front of the day side, and then here you have the magnetotail, which is extending far beyond the Earth. I will tell you the dimensions a bit later. It has a northern lobe and a southern lobe. Here the field lines come towards the Earth, and here the fields go away from the Earth. And between the two lobes you have kind of a plasma sheet where the magnetic field is very weak and you have a higher density. And then, well, the last part is this orange part is the the plasma sphere, or also called the inner magnetosphere, which consists of low energy cool plasma. It's located above the ionosphere. You will hear about the ionosphere later this week. And the boundary is actually defined as an order of magnitude drop in density. And the particle motion is determined there entirely by the magnetic field of the Earth. It co-rotates also with the Earth. Now, I mentioned magnetic reconnection before. This is a kind of a generic mechanism that rearranges the magnetic topology and converges magnetic energy into kinetic energy or thermal energy and particle acceleration. It involves plasma flows. There's at a substantial fraction of the Alfvén wave speed that I mentioned. The Alfvén wave speed is a fundamental speed for mechanical information flow in magnetized plasma. And here you see an illustration of how magnetic reconnection kind of changes the topology of the magnetic field. So there's two separatrices here, the diagonals of this square. And so the field lines, there's plasma flowing from the top and from the bottom towards this X point, and there the magnetic field lines reconnect. And magnetic reconnection is a generic process, and the concept of magnetic reconnection was actually discovered in parallel by solar physicists and researchers that were studying the interaction between the solar wind and the magnetized planets. And so this kind of reflects the bidirectional nature of the reconnection. So it can either disconnect formally connected magnetic fields, like in a solar flare or in a CME, or it can connect or reconnect formally disconnected magnetic fields, like the magnetic fields of the solar wind and the Earth in this interaction. Now, I promised to mention something about the dimensions of the magnetosphere, and I'm going to use this illustration to do so. So at the day side, the magnetic field is considerably compressed by the solar wind, and this size is here about 65,000 kilometers. And the Earth bow shock is about the bow shock here is about 17 kilometers thick on average, and it is located about 90,000 kilometers away from the Earth, so like 15 solar radii. Earth radii, sorry, of course, Earth radii. Okay, then the magnetopause allows the solar wind particles to enter, and this causes Kelvin-Helmholtz instabilities, like you can see here in this simulation from Delamere et al. Recently. And so the plasma travels at different velocity at the edge of the magnetosphere, and so then you get this shear in the velocity that gives rise to the Kelvin-Helmholtz instabilities, and by which the particles can enter the magnetosphere. And of course you have to see it in 3D. This is a kind of a 3D, more complicated image, also showing the currents in the magnetosphere. And the reconnection events can occur, of course, enabling particles from solar wind and to enter the magnetosphere. The magnetotail, so at the backside of the Earth, is kind of very long, more than 6,300,000 kilometers long, and this is the primary source of the aurora, as I will show you later. Because the interaction of the solar wind with the magnetosphere actually depends on the polarity of the interplanetary magnetic field. And here I chose I think one of the earliest illustrations from Dungey, already from 1961 and 1963. It is an early 2D representation of the reconnection between magnetic fields of the Earth and the solar wind. And here you see when the interplanetary magnetic field is at the same polarity as the magnetic field of the Earth, and then the reconnection is actually occurring here at the sides here, at high latitudes, just downstream of the Earth. But the most dangerous situation is the opposite case, when the interplanetary magnetic field polarity is opposite of that of the Earth. Because then you have reconnection here at this X point here, but also here in the magnetotail, and this is causing the aurora. So this is illustrations that are from Dungey, but I borrowed them from Russell, well, actually from a paper from Tratner et al., who borrowed them from Russell, so it's borrowed. Okay, so here is an illustration, a movie that I found on the internet from NASA, showing what happens with these particles that are accelerated by a solar flare. It's of course an artist impression. So here you see the sun, and you will see a solar flare, and then there's a magnetic cloud with charged particles, high energy particles, that is actually launched in the direction of the Earth. Here you see the deformed magnetosphere, and then you see how this is a case where the magnetic field is the opposite topology of the magnetic field of the Earth, and then you see how this reconnection in the magnetotail causes the aurorae. Here it is kind of nicely illustrated to have an idea of how it works. So let's recuperate a bit. What did we learn so far? The magnetic field of the Earth shields the planet and its atmosphere from the solar wind, but the shielding is not perfect, to say the least, and a fraction of the mass and energy and momentum of the solar wind can transfer to the magnetosphere and the ionosphere through processes that are often referred to as solar wind magnetosphere interactions. Now, there was a recent paper of Pulkkinen et al. That performed many different simulations, 131 simulations of geomagnetic storms using the space weather modeling framework from Michigan. And they were focusing on modeling the parameters that are characterizing the condition of the magnetosphere, like the geomagnetic indices, and they kind of show that they are related to the solar wind drivers, the magnetopause locations, and the cross polar cap potentials. So they kind of claim in the paper it's a good way to quantify the interaction of the solar wind and the magnetosphere. So we will focus a bit on these, well, on some of the geomagnetic indices, not all of them. And the first one to focus on is the DST index, the Disturbance Storm Time Index, the Kyoto DST, also called, introduced by Sugiura in 1963. And this gives information about the strength of the ring current that is caused by solar protons and electrons, and it has a large effect on the electrodynamics of the geomagnetic storms. The ring current that was illustrated in this 3D image that I showed before, so here's the ring current, yeah? So it is kind of a band, so it's in a band at a distance of 3 to 8 Earth radii, lying in the equatorial plane and circulating clockwise, if you look from the north at least. And so the ring current produces a magnetic field that is directly opposite to the magnetic field of the Earth. So the stronger this ring current is, the weaker the magnetic shield of the Earth. And this, yeah, the weaker it gets is indicated by or quantified by this DST index. So it's a negative index. The more negative DST, the weaker and the heavier the storm is. And so, as I said, a negative DST value means that the Earth magnetic field is weakened, and this is particularly the case during solar storms. It's kind of, there are 4 observatories around the Earth, and it's kind of an average. They measure the local variation of the horizontal component of the magnetic field, yeah? And so they kind of, this gives so they are kind of averaged. So this is the local variation at this particular station. This is the latitude of this station, so kind of they take into account the latitude as this cosine of latitude, because it's the ring current is in the equator, of course. And so this kind of gives a rough average of the global horizontal variation of the magnetic field. Yeah? This is the first geometric index. Another one is, another important one is the KP index, which was introduced by Bartels in 1939 to quantify the geometric activity. And this is an integer between 0 and 9. And 1 means very calm, 5 and more means geometric storm. So it's directly, this is why I like this parameter, it's directly linked to the storm. The storms are classified, there are 5 different scales or categories of storms, G1 to G5, and G1 corresponds to KP value 5. Yeah? G2 is KP value 6, G3 is 7, 4 is 8, 9, and 5 is then the most severe storms, KP index 9. So they are derived from the largest, the KP index is derived from the largest fluctuations in nanotesla relative to a quiet day of the horizontal components of the magnetic field also of the Earth with 3-hour intervals. And then there's the auroral electrojet indices, the A indices, AE, AL, AO, and AU. The AE index is a proxy of the response of the ionosphere to the substorms, which are kind of which are quite stochastic, and they have a high temperature variability. And so these are also derived from geometric variations in the horizontal component of the magnetic field observed at selected observatories, like 10 to 13 different observatories along the auroral zone in the northern hemisphere. And we have the AU and the AL indices, respectively defined as the largest and the smallest of these normalized values selected from all these stations. The symbols AU and AL are the A upper and A lower, the kind of the values of the upper and lower envelopes of the superposed plots of all the data from these 10 to 13 different stations as a function of the universal time. And the difference between these two, AU and AL, is called the AE index, and the mean value of AU and AL, so AU plus AL divided by 2, is called the AO index. But the term AE indices is often used to represent all 4 of these indices. I will come to that later. So now we try to kind of compute these indices, or to predict how these indices are going to vary. You can measure them, of course, but you can also try to predict them. And to do that, we use, in Leuven, we use the code EUFORIA, which is an acronym for European Heliospheric Forecasting Information Asset. You will hear a lot about EUFORIA later, tomorrow, I think, in the lecture from Michaela. It consists of 2 parts. There's a simple coronal model, Wang-Chili arch-like, so a semi-empirical model, and then there's a heliospheric model from 0.1 AU till 2 AU or further. It's just a parameter in the model. And here you see it's a 3D MHD model of the solar wind, and here you see kind of an illustration. I should use this one. Some illustration of the radial velocity and the density in the equatorial plane and in the meridional plane of the Earth. The blue dot is the Earth, here and here also. And so this is in HEEQ coordinates, so the longitude of the Earth is always the same. And then here you see different planets. This is Mars, this is Mercury and Venus, and this is satellite, Solar A, I think. And so you can actually see where the wind is. You can, of course, extract the data at any of these points, wherever you want in the heliosphere. And so these are projections, or these are cuts, I should say, in the equatorial plane and the meridional plane of the, as you see then the wind, the spiral structure of the wind, and on top of it you can launch CMEs, depending on the parameters that you observe, and then you can kind of predict when it will arrive at Earth. And so here you see kind of a typical case. Well, actually not typical, it's the first case we did with EUFORIA. And so you see here on the bottom, in red, the measured value at L1, just before the Earth, and in blue, the simulated value. You see different shocks. There were 6 CMEs that period. And you see here the first CME is coming out a bit too late, and the shock is very diffuse in the simulation due to too low resolution. The second shock is way too late in the simulation, a couple of hours too late. The third shock is just a bit too late, it is the right size, and the fourth shock is actually exactly on time in the simulation, but it's twice too strong. So there's room for improvement, luckily, so otherwise we would be out of a job. So this is a kind of the, well, it's not the current state of the art, because these were very simple CME models. You will hear about that later this week. But we kind of can predict the solar wind at the L1. So this means that we can actually also, when we have a model for the indices, also kind of use the synthetic data at L1 instead of the measured data to kind of compute the, or predict how the indices will evolve in time. Another way to do that is to connect the heliospheric code with a magnetosphere code, like OpenGCM. There are other codes, of course. There's Leuven, there's PITHIA-NRF from Michigan. OpenGCM is actually from New Hampshire in the United States, from Jimmy Rader, and Gorgon Space also. So there are very good models. OpenGCM is one of the better ones, and it's coupled already to Euphoria, and so is Gorgon Space and Gumix. Gumix is also coupled to Euphoria. So what we did is we kind of coupled the two codes. That means that we use synthetic data at L1 instead of the measurements. That normally these codes, like OpenGCM, are operated using synthetic data at L1, and then they kind of predict the reaction of the, or they compute the reaction of the magnetosphere to this wind data. But this is kind of not really a forecast. It's called a nowcast, because when the wind is already at L1, it will be 2 hours later at Earth. So this is not very much in front or before the actual event happens. So of course, if we can predict the wind 2 days earlier from Euphoria and use this synthetic data, we can actually also predict the reaction of the magnetosphere 2 days earlier. And that's what we try to do here. So we coupled Euphoria to OpenGCM, and then the OpenGCM actually computes also the geometric indices like DST and AE index. And here you see one of the early results we had in, well, it's actually a paper that is just submitted. It's not even published yet. It hopefully will be published soon. Here you see the modeling. So it's not perfect, of course. So in black again is the observation. In blue is the synthetic data from Euphoria, 2 days earlier, of course. And so you see the shock is arriving a bit too late in this case. The second shock is too early compared to this here. The density is a bit too high with Euphoria, and the BZ component is almost the right magnitude. It's also a bit too early, but it has the right profile, let's say. So now when you use these data in blue to drive OpenGCM, you can actually compute the DST index and also the AE indices 2 days ahead of time. And so here, these are a bit complicated plots. In red is the measured DST, like the formula that I showed before. In black is the normal operation of OpenGCM, this magnetosphere model with the using this red line as input, the black here as input data. And then you can get this prediction of the DST with nowcast of the DST. And if you use the synthetic data from Euphoria, we get the blue line here, which is not as good, of course, but 2 days earlier. Yeah, this is for DST. It's too negative here with the synthetic data. This is for AU and AL, and so this results in this AE, and you see the AE index is underestimated in this simulation. It's not always the case. It depends, of course, how good you can predict the wind, and especially it's not so simple, especially when there are CMEs on top of it. So you have to kind of try to improve these predictions at L1. This is a different case, second event, where we have this kind of fit, and here you see different, slightly better prediction of the DST index, and also for the AE index a bit too early in the simulation. But mind you, it's of course less accurate than the nowcast, but it's 2 days ahead of time. So what we constantly try to do is to improve the synthetic data at L1. And for the wind, we try to improve the coronal model. Michaela will tell you all about it later, well, tomorrow. And so an important thing is the polarity of the interplanetary magnetic field upon the impact of the CME, as I mentioned before. So especially the BZ component, when it is negative, it has a larger impact. So we try to predict this BZ component, because we need good flux slope CME models, and that's what we try to do to import now or to implement in Euphoria. And one of the best models we have so far is called the flux slope in 3D. It is called. It was developed by Alexei Isavny in 2016. It has been integrated in Euphoria, and it is kind of a rather advanced model. And so we integrate, and here you see 4 snapshots of a kind of an evolution of this model all the way up to Earth. The dot here is the Earth. You see it arriving, and we try to predict the internal magnetic field of the CME as it arrives. That is quite a big challenge, of course, to do this correctly. But sometimes we are successful, and sometimes we are less successful to do this. Here, for instance, you see the comparison. Well, a simpler model is a sphermac, just a sphere with an internal magnetic field. And here you see a comparison between a sphermac model and the Fry2D in red. So in black is again the measurement at L1. In red is the prediction of a sphermac CME, and in blue is the prediction with a Fry2D CME. Here you see the velocity. The Fry2D arrived a bit too late because we don't know how to put the parameters correctly yet. We're trying to improve it. The density is more or less okay. The BZ component is much better with the Fry2D CME. It arrives too late. That's true, because the shock arrives too late. That's why the BZ component goes down too late. But you see it is the right magnitude. So it should kind of, you can already expect from this that the DST prediction will be better. And here you see a DST prediction indeed. With the sphermac it was very bad, but with Fry2D it starts to go down too late, but it goes again to the right magnitude, like kind of minus 100, which is also predicted by the synthetic data from Euphoria, but well, a couple of hours too late. And KP was also like kind of much better than the KP index predicted from the sphermac model. So we are kind of getting there to kind of quantitatively predict these indices, not always with the same accuracy. Now these things can be done in the Virtual Spatial Modeling Center. You will hear also about it later this week, and there's actually one of the working groups will be about Euphoria within the Virtual Spatial Modeling Center. This is an open end-to-end Sun-to-Earth spatial modeling system that enables interactive runs of different models, like 20 models at the moment, and you can also, the models are coupled to each other, so you can use them very easily. You can enter the Spatial Modeling Center via the e-center from PITHIA, and I think they will show you later this week how to do that, especially the group that will use it. And anyone can access this system now, and you can also use the models. And why am I saying this? Because there are many model chains in the modeling center, and some of them are actually coupling Euphoria, so for the 2 parts of Euphoria, with these models for the DST and the KP index, and also the plasmasphere standoff distance actually. So here the models are described in the system. They will show you later how to get this information. And so, in fact, these are not the data, of course. These are actually models that kind of predict DST index and the KP. Very simple empirical models. And the empirical DST model is the model from O'Brien and McFerran from 2000. This is a corrected DST index. So this is the corrected DST index with this term, depending on the force exerted on the magnetosphere by the solar wind, the dynamic pressure of the solar wind, and another correction term. And so they have a very simple differential equation to describe the evolution of this corrected DST index. By this Q is proportional to the rate of energy injection into the ring current, which is very important for the DST, as I mentioned before. And then there's also this tau parameter, which is kind of a decay time varying between 3 and 20 hours. You can do a very simple forward difference for this to solve this differential equation, but you have to solve the differential equation, but it goes very fast. It's an ordinary differential equation that just takes half a minute or so. And then you can have a prediction of the DST index. And this works fairly well, of course, depending on how good you can provide synthetic data. Here, for instance, you see case where we use a spheromac again, but now we played a bit with the parameters and we have a perfect arrival time. This is actually also, we try to kind of quantify the uncertainty, so we take not only a position at L1, but also some positions around it, yeah, to kind of take into account the uncertainty on the input parameters of the CME. And so this is the simulation, so the synthetic data, in the blue are the measured data, and in red you have the synthetic data from the simulation. And you can see here the DST, the measured DST value, and here the predicted DST value. And you see we were a bit too high here because of the effect of the pressure was badly predicted here. We think that we are investigating why this is, because it's a very recent result. One of my master's students, Stefaan Poedts, is doing these simulations. And he thinks that because of the bad prediction of the pressure, that we are here overestimating the DST value. But you see, you can actually quantify these things and you can make quantitative predictions of this. It's not always this good, of course. So here you see another case where he has, again, well, worse simulations of the synthetic data are worse. And you see here, for instance, the DST is twice too negative. So it's not always the case, let's be honest. The previous one was a typical case, as they say. No, it's sometimes good, sometimes bad. So again, room for improvement. And similar to the DST, we also have empirical KP models. In the modeling center, there's the model of Newell et al. From 2008, where they used kind of 32 different solar wind coupling functions, like the dynamic pressure and etc. They make many different combinations and then do kind of statistical analysis, and they take the least variance linear prediction, which comes up with this formula. This time it's not a differential equation, but the formula, where this is the rate of magnetic flux is opened in at the magnetopause. And so then you have all these other parameters, the density, the velocity, the total magnetic field, the Z component is also playing a role. So all these parameters that you simulate, you can be used to evaluate this formula, and then you can also predict the KP index. And again, we use the same simulation as before. This is exactly the same as before, and you see that the KP index is actually very well predicted by this model 2 days ahead of time. Yeah. It's not always as good. Again, the other simulation is the other event in 2017 here. We had a worse simulation and therefore also a worse prediction for the KP index. So this is actually ongoing research here that we try to make to improve these predictions, of course. And we are trying to also use other empirical models. There's the NARMAX models, which are also integrated already in the modeling center, as you will see when you do it yourself. And there's also a kind of feed-forward neural networks from Peter Wintoft and Magnus Wick, very recent models that kind of use recurrent neural networks, and they have different formulas. Here you see the most simple one is this Elman network, but well, we are doing this now together with Peter Wintoft, and we try to also see how we can improve actually the predictions of these indices. And there, the problem is that in this the pause, the magnetosheet between the shock of the CME and the magnetic cloud, you have these erratic variations of the magnetic field, which are not random. There's kind of physics in it, and we are trying to include this physics in the simulations now, using smart noise. And this is the subject of this thesis of the master thesis of Stefaan Poedts. So this is ongoing research. I cannot tell you more because we did the simulations already, but we are now analyzing the results of these recurrent neural networks to see how good or bad they predict the indices. So, where are we? What are the take-home messages of this lecture? Well, I think these. So the space weather has a large socioeconomic impact. Modeling is difficult because it's a multi-scale, multi-physics problem, and it's extremely challenging, especially the solar wind magnetosphere interaction, because it depends crucially on this Z component of the internal magnetic field of the CME, which is difficult to predict, of course, because it's often different from what is measured when the CME leaves the sun. Yeah? And so this is 150 million kilometers. It's very difficult to predict that accurately, but nevertheless, we will have to do it if you want to improve the prediction of the impact of the CME at Earth. Some of these problems have models with predictive value, and so as you will see in the modeling center, we can actually chain these models. We have several sun to Earth model chains that can actually do better than nowcast in the sense, well, not necessarily better, but certainly earlier than nowcast, like 2-3 days in advance, do simulations and predict how the DST or how the magnetosphere solar wind interactions will evolve. So, of course, as you've seen, the predictions are not perfect, so there's a lot of modeling works that remains, and especially the wall clock time, so how long it takes us to do the simulation is very important, and so we try to speed up the simulations by using, developing new numerical techniques. This is actually one of the subjects of the team we have here in Leuven. We try to speed up the simulations as much as possible. Thank you for your attention. Are there questions? Wow. It must have been very clear. Apparently. No questions. Okay. Then I think we can go for coffee. Then we can go for coffee. Okay, let's go for coffee then.
The next talk is at 3:30.
3:30, yes. I will stop the recording.